Hey everyone, welcome to today's Explainer. I'm genuinely so pumped to have you here. Look, let's be honest for a second. If you've ever stared at a chaotic page of algebraic equations, the ones with the letters and numbers all mashed together, and felt your heart rate immediately spike, you are in exactly the right place. Today, we're going to completely reframe how you look at algebra. We're going to take what looks like a tangled, intimidating mess, and we're going to transform it into a simple, highly systematic toolkit. By the time we wrap up this explainer, you'll see that complex algebra, it isn't magic. It's really just a set of specific, reliable tools. And once you master this toolkit, you'll be able to represent and manipulate virtually any mathematical problem with total confidence.
Okay, let's kick things off with a little challenge. Picture this. How would you solve 13 squared minus 7 squared in seconds, purely in your head, without touching a calculator? For most of us, the immediate instinct is to just buckle down and do the heavy lifting, right? You'd calculate 13 times 13, which is 169. Then you'd figure out 7 times 7, which is 49, and then very carefully subtract them. I mean, sure, it works, but it's slow, and honestly, it's pretty easy to make a silly mistake. But what if I told you that the structural rules of algebra actually give us a massive shortcut? A shortcut that makes solving this an absolute breeze. Keep this exact problem in the back of your mind, all right? Because we're going to use our new algebraic toolkit to unlock it in just a few minutes.
So here's our game plan for today. We're going to start off with expanding expressions and factorization, laying down the groundwork. Then, we'll move into the heavier stuff, solving quadratics and cubics. After that, we'll look at a really powerful skill, changing the subject of a formula, before we finally tackle the ultimate final boss, algebraic fractions. Let's get right into it.
All right, Phase 1, building and deconstructing. Let's talk about expansion and factorization.
I want you to think of expansion and factorization as literally two sides of the exact same coin. When we expand something, we are basically building a mathematical structure outwards. Take the perfect square, for example. This happens when you multiply two identical brackets together. So let's say we have x plus 4 multiplied by x plus 4. The rule here is incredibly simple, but it is strict. You have to multiply every single term in that first bracket by every single term in the second bracket. Okay, so x times x gives us x squared. Then x times 4 gives us 4x. Moving to the next term, the 4 times x is another 4x. And finally, 4 times 4 is 16. Now, just combine those two middle terms, the 4x and the 4x, and we land beautifully at x squared plus 8x plus 16. Boom. You've just built the structure out. Now, factorizing, that's just putting that exact same process into reverse gear. And this is where it gets really, really cool. If we expand x plus y times x minus y, something basically magical happens. You do the multiplication, but those middle terms you get, a positive xy and a negative xy, they completely obliterate each other. They cancel out to 0. So you're left with just x squared minus y squared. So working backwards, if you ever spot a squared term minus another squared term, a pattern we call the difference of two squares, you instantly know how to break it down. It will always factorize into two identical brackets, just with one having a plus and the other having a minus. It is a universal mathematical law.
Okay, so let's circle back to that seemingly impossible mental math question we started with. 13 squared minus 7 squared. Do you see the pattern now? It is literally the difference of two squares. It's one number squared minus another number squared. So rather than doing all that messy arithmetic we talked about, we just grab our factorization tool. We pop those numbers straight into our brackets. 13 plus 7 multiplied by 13 minus 7. Well, 13 plus 7, that's a perfectly round 20. 13 minus 7, that's 6. What's 20 times 6? 120. Solved in seconds, all because you recognize the underlying algebraic structure. That right there is the power of the toolkit.
Moving right along, let's bring out the heavier machinery in Phase 1.5, solving quadratics and cubics. So what is a quadratic? It's simply an algebraic expression where the highest power is a squared term, like x squared. Now, I know they can look a bit intimidating, but they're actually incredibly predictable, especially if you use a brilliant visual tool like the 2x2 grid method. Let's say we need to factorize x squared plus 5x plus 6. We know it originally came from two brackets multiplied together. So in our grid, we place our x squared in the top left box and our constant, the positive 6, in the bottom right box. Well, what multiplies to make x squared? Just x and x. Easy. Now here's the real puzzle. We need to find two numbers that multiply together to give us that positive 6, but also add together to give us our middle term, the positive 5x. Take a second. Positive 3 and positive 2 are the perfect fit.
Because 3 times 2 is 6, and 3x plus 2x gives us our 5x. So, our deconstructed original brackets are simply x plus 3 and x plus 2. It's just like solving a Sudoku.
Okay, but what if they try to trick you and throw a cubic expression your way? Something like x cubed plus x squared minus 2x. The highest power there is a 3. Total panic mode, right? Actually, no. Look really closely at it. Every single term in that expression has an x in it. So your step 1 is incredibly simple. Just pull that x right out to the front. And when you factorize out that single x, look at what gets left behind inside the brackets. X squared plus x minus 2. It's just a friendly, familiar quadratic hiding inside. And you already know exactly how to solve that using your grid method. You just turn the chaotic cubic into a simple quadratic.
All right, we are rolling. Welcome to phase 2, the master key. We are going to talk about changing the subject of a formula.
Changing the subject of a complex formula is simply about isolating one specific variable so it stands completely alone on one side of the equal sign. Honestly, I like to think of this as unwrapping a present. Here we've got x squared plus y squared equals h squared. What if we want to make y the subject? Right now, it's all tangled up with the x squared. We have to unwrap it by performing the opposite operations, making sure we keep the equation perfectly balanced at all times. First things first, let's subtract x squared from both sides to just get rid of it on the left. That leaves us with y squared equals h squared minus x squared. Better, but y is still squared. And what's the opposite of squaring something? Taking the square root. So we square root both sides, and we are left with y equals the square root of h squared minus x squared. You just systematically peel back the layers to isolate your target. Let's look at a much more intimidating example just to prove that this unwrapping method literally never fails. We have m equals 3a squared p all divided by x squared, and we need to make x the subject. Right now, x is trapped way down there in the denominator. Step 1, multiply both sides by x squared to rescue it and bring it up to the surface. Now we've got x squared times m, but we need x squared completely alone, so we divide both sides by m. Now we're looking at x squared equals 3a squared p over m. We are almost there. The final unwrapping step? Just square root the entire other side to get rid of that square on the x. Listen, if you systematically extract and move the terms using opposite operations, you can literally bend any equation to your will.
Which brings us to phase 3, the final boss, mastering algebraic fractions.
So we have arrived at the topic that usually terrified students the most. But before you get nervous, I want to reassure you right now. You already possess every single tool you need to defeat this final boss. The absolute most crucial point to remember is this. Algebraic fractions obey the exact same universal rules as the simple numeric fractions you learned years ago. There are 0 new rules here. It's just different characters playing by the exact same script. You still have to find a lowest common denominator to add or subtract them, and to simplify them, you just use the factorization skills we literally just mastered back in phase 1.
Let me prove it to you. Consider a standard numeric fraction, 4/11ths plus 3/11ths. The denominators, the bottom numbers, are exactly the same, right? So we just add the numerators across the top. 4 plus 3 gives us 7/11ths. Simple. Now look at the algebraic version right next to it, a over 11 plus b over 11. Because the denominator is the same, the exact same logic applies. We just add the numerators across the top to get a plus b, and the whole thing sits over 11. See? The letters don't change the rules at all. They are literally just holding the place of numbers. Okay, let's step it up a notch. What if the denominators are different? Let's say we have x over 3 plus x over 4. Just like with regular everyday fractions, you cannot add these until the bottom numbers match. We need to find the lowest common multiple of 3 and 4, which is, of course, 12. So we multiply the top and bottom of the first fraction by 4, which gives us 4x over 12. Then we multiply the top and bottom of the second fraction by 3, which gives us 3x over 12. And look at that, the denominators match perfectly. So we just combine our numerators, 4x plus 3x equals 7x. Our final, elegant answer is just 7x over 12. You aren't doing crazy advanced math here, you're just bridging the gap using standard arithmetic principles. All right, let's move to our final challenge and see how absolutely everything we've learned builds together. We need to simplify this beast, x squared plus x minus 2 all over x squared plus 2x. It looks awful, I know, but remember our phase 1 toolkit. We can factorize to deconstruct these expressions. The top part is a quadratic. Using our grid method from earlier, that factorizes neatly into x plus 2 multiplied by x minus 1. The bottom part is even simpler.
We just pull out the common x, leaving us with x times x plus 2. Now, step back and notice what we have. An x plus 2 bracket on the top and an identical x plus 2 bracket on the bottom. So what do? We cancel them out. They completely obliterate each other. The entire terrifying fraction collapses down into a beautifully simple result, x minus 1 all over x. Bam! We used our whole toolkit to completely dismantle it.
And just like that, we've made it to the end of our journey today. Think about what we just did. We took equations that looked like pure, unadulterated chaos, and by using really simple, systematic rules like expanding, factorizing, unwrapping formulas, and applying basic fraction logic, we turn them into easily solvable puzzles. Which leaves me with a thought I really want you to carry with you today. If complex algebra is truly just a puzzle that you can solve by applying systematic rules, what other chaotic, overwhelming problems in your life can you step back from, deconstruct, and break down the exact same way? Give that some thought. Thank you so much for joining me today. Keep practicing with that toolkit, and I will see you in the next explainer.